Kia ora. This is the last video I'm going to do tonight, and this one is from the integration exam as well. And it's one where you've got to find the area bounded by three graphs. It's a really nice question as long as you go slowly. And we've got three graphs in here, or three functions in here. The first one is the one that might have freaked a few of you out, which is y squared is equal to 10 minus x. But you can see that what we've got here is a parabola. And we want the top branch of that parabola. So we can rewrite that as y is equal to the square root of 10 minus x. If we were dealing with this bit here, it would be y equals negative root 10 minus x. But it is completely irrelevant in this question, right? So we don't need to worry about it. So what does that leave us with? Well, we're going to use the result that when we want the area between the two curves, and we've got some of it is underneath the x-axis. But the happy news is that when we're working with situations where we're looking at the area between two curves, we can just do this. And I'm not going to go through in this video why that works. I've done that in class. But that's what we're going to use here. So what this question then comes down to is figuring out what's this point, what's this point, and what's this point. And then we're going to do two separate integrals. We're going to do one here, and then let me change pen color, something nice. Then we're going to do the other one is going to be this one here. And both of these intersection points are actually really nice values. I think the main thing to do with problems like this, and it is really hard when you're under time pressure, is not to rush it. So when I did this one, miraculously, I didn't make any little mistakes, but it's very easy to do that. So what I suggest you do is that you just get in the habit of checking each line as you're going, or at least checking after every couple of lines that you haven't mucked something up. Okay, the first thing I'm going to do is just label this one F, this one G, and this one H. And we've got y is equal to the square root of 10 minus x, that's F. Y is equal to 3x, that's G, and y is equal to negative sine of pi x on 10, and that's H. So let's first figure out what this point is. Well, that's pretty easy. That limit's going to be 0. Now, what about this one here? Well, let's set 3x equal to the square root of 10 minus x. You can just about see this one from looking, but if you're just doing this with algebra, we're going to get 9x squared is equal to 10 minus x. So 9x squared plus x minus 10 equals 0. Look, it looks like 1 is going to work. So let's just have a look and see if 1 will work. Well, 3 1s are 3, and 10 minus 1 is 9, and the square root of 9 is 3. But if you didn't spot that, and I think when you're under pressure, you're less likely to spot that, we can either chuck this into our graphics calculator, and yes, I did actually just say that. Yes, chuck it into your graphics calculator and look at the roots, or very easily have a crack at factorizing it. X minus 1 goes in straight away, right? Because we get 9x squared here plus 10x minus 9x minus 10. And so that tells me that this point here, because it's the positive root, is x equals 1. So that's going to be at point A, right? And then this one down here is really easy because it's the place where y is equal to 0. So that must be happening where x is equal to 10. So sometimes in these questions, a lot of the work I've seen some level 3 questions where it feels like you're doing all the work as algebra to find those intersection points. I feel like this question was quite nice and that balance was about right. You had to think a wee bit, especially about this, but then it was pretty much smooth sailing from there. So that means that now I'm going to find two areas. I'll just shrink it a little bit so I can draw on here. And a good thing to do is let's just mark this as area 1, and this bit here is area 2. So the total area is going to be the integral from 1 to 0 of the top function, 3x, minus the bottom one, which is negative sine of pi x on 10. Just note that this is the pattern f of x minus g of x, and this whole thing is negative. And then we're going to have plus area 2, which is the integral from 10 to 1 of the top function. Remember, that's equal to y equals square root of 10 minus x. I'm writing that with a fractional power because I'm about to integrate it, minus negative sine of pi x on 10 dx. Okay, so several ways to go here with your working. You can either do those two things separately, but some stuff is probably going to cancel out. So I just did one big kind of double integral, and I didn't evaluate stuff too early. So in here, I've got 3 over 2 of x squared, and I'm going to have cos of pi x on 10. When I differentiate that, I'm going to get pi on 10 coming out. I don't want that, so I times by the reciprocal. And I'm also going to get negative sine, but I want positive sine. So I need to have minus in here, and that's evaluated at 1 and 0. And then for the next one, well, it's going to be 10 minus x to the power of 3 over 2. I have to undo the 3 over 2, and I also have to undo a negative 1 from the chain rule when I differentiate back. Here I've got plus of this, so again we're going to have minus 10 over pi cos of pi x over 10. And that's evaluated at 10 and 1. Right, so just moving through this, quite a lot of things are going to go, and we'll have 3 over 2 times 1 minus 10 over pi cos of pi on 10 minus 0 minus 10 over pi cos of 0. So that's the first one, plus. Right, now just thinking again nice and slowly here. When I substitute that 10 in here, that term's going to be 0. So 0 minus 10 over pi cos of pi. Right, so just being really careful with your trig substitution here. We've got 10 here, x here, and 10 here. So that's how I get cos of pi here. And now I need to take off the lower limit, which is going to be minus negative 2/3 times 10 minus 1 is 9, so 9 to the power of 3 over 2, minus 10 over pi cos of pi on 10. Right, so I'm doing this basically exactly how I did it when I grabbed the paper 5 minutes ago. And some of you might have cleaner ways to do this. But let's just see what starts to drop out now, because it's quite nice. So 3 over 2. I'm going to write it out distributing all of my negative signs. So I've got minus 0 here, and then I've got plus 10 over pi. Remember that cos of 0 is equal to 1. So that's just plus 10 over pi. And now I've got minus 10 over pi. And in here, this is, so what's cos of pi? Well, cos of pi is down here at negative 1. So it's minus 10 over pi times negative 1 plus 2/3 of 9 to the power of 3 over 2 is the square root of 9, 3. 3 cubed is 27 plus 10 over pi cos of pi on 10. So happily, where's my pen gone? Happily, we can see that this goes, and I'm sure some of you just grabbed your calculators at this point. Never mind, that's fine. But I just worked through this to get an exact value. So I've got 3 over 2 plus 10 over pi, 2 lots of those, plus 18. And when I put all that together, I get 19.5 plus 20 over pi. And getting an approximate value for that gave me 25.8662. So I was worried with this one that I didn't want to do a video on it and screw it up. So I have gone and checked that with GeoGebra, and it's pretty cool. That's exactly what we get in GeoGebra, and this is what it looks like. So you can see in here that here's my first area here that we've got. So that's what we would get if we did the first integral separately, which I'm sure some of you did. And then this 24.211 is the second one. And when you take that number and you add them up, you get our number, which is 25.8662. So thanks for watching till the end if you did. If you're watching this and you haven't just sat the exam, so if you're watching this sometime in 2024, I think this is a really good question to just go through how to do kind of long, mucky substitutions near the end of the question. So overall, I really liked this question. I think this was a good level for excellence. It's probably on the slightly easy side for an excellence question, honestly, but it still was testing whether you had a good understanding of a couple of things, especially this idea that we've got the top function here and the bottom function here, and that we could split the integral up into two separate regions.